Hello there. Welcome to our today's science lesson. The topic for the day being description of solids, liquids, and gases. You realize that in our previous lesson, we talked so much about substances, and in particular, looking at our immediate last lesson, it was a description of substances in terms of how to choose which material to be used with respect to physical and chemical properties of the substance. But we also need to understand that these substances we talk about, whether it will be involved in a physical change or a chemical change, that substance has its own story to tell about how it behaves the way it is, how it is the way it is. Whether it's a solid, a liquid, or a gas, there is a big story behind it. And in our today's lesson, we are going to partially look at it, which we shall continue with the same in the coming lessons. So we want to look at when we talk about a solid, when we talk about a liquid, when you talk about a gas, what are you talking about exactly? What is that solid? And what is the difference between these three properties of three states of matter? Remember, these are three states of matter. I remember having stated the three states of matter. Though I also added there another one called plasma, where I said that one only exists under special conditions of a temperature above 6,000 degrees centigrade. And you can imagine, if you want to know it's an extreme temperature, just look at what 100 degrees centigrade of boiling water can do to you. Then imagine of 6,000 degrees centigrade. I'm sure it is extraordinary. That's plasma. So for us, we limit ourselves to three states of matter, that is solids, liquids, and gases. Now, we need to understand that each of these three states of matter has its own characteristics, has its own properties. And there are the very properties that we normally use to categorize them or to classify them as these are gas, these are liquid, and this is a solid. So, for us to understand solids, liquids, and gases, just like what other scientists do in whatever areas of their study, they always use what we call models. They always use what we call models to understand aspects. That is what we are going to do. We are going to look at models which will help us understand what is a solid, what is a liquid, what is a gas, what are the similarities, and what are the differences between these three states of matter. Maybe to go deep a little bit into models, before we go specifically to the three states of matter, we have two types of models. We have two types of models. Two types of models, that is models in science. We have two types of models in science. And the models, before I give out the types of models, this is a kind of a solid descriptive way of something that could be very big for somebody to comprehend on the way it exists, it operates, it is made, and all that, or that item or that aspect you are trying to describe is too small for anyone to comprehend how it is, how it operates, or how it exists. So a model is just a physical arrangement, a physical description simulating what you already know or what you are trying to imagine on how it operates. Maybe as I look at the two types of models and give examples, you will try to understand much better on what I'm trying to say a model is. So there are two types of models. The first model is analogous or analogies of the models. So number one are analogies or analogy. Analogy, it means we are talking about a single one, just one, but analogies means so many. So these are the types of models that you can easily interact with. These are model or a performing item that you can easily interact with, that can easily be used to describe something that is a little bit incomprehensible. For example, you and me, we both have a heart. Mine is here. You can touch where it is. Are you feeling it? Try to feel it. You can only feel it comfortably when you're quiet. Yes, I'm feeling the heartbeat. Now, what is that heart doing by you feeling the heartbeat? The obvious answer is it is making the blood in your body to move around. Oxygenated blood to go where it's supposed to go, to supply the oxygen, and deoxygenated to go where it's supposed to go, to collect oxygen, and the system continues forever until that day the maker calls you. But now, this is something you cannot see. I can only manage to feel it. But I will wish I as an individual, I'm not a doctor, and even if I'm a doctor, and maybe you are not a cardiac specialist, you may not understand in proper details of this heart. But at one time, you will want to know how this heart operates. So if somebody will want to explain, assume you are explaining to a layman on how a heart operates, you will need an instrument, an apparatus, a machine that is around us that you can easily use to try and explain to that person to understand. And that thing is a water pump. A water pump, if you can assume this is the water pump, it will have an inlet and it will also have an outlet. The inlet will come in but with less pressure, but the outlet will go out but with the contents in the outlet will be going out at high pressure. And this is what happens in the heart. When blood is coming in from, let's say oxygenated blood is now coming in from the lungs, that is we have arteries and veins. The only vein that carries oxygenated blood is the one that is coming from the lungs. So once it enters the heart, it may be coming in with some slight pressure, but once it goes out through the aorta. Aorta is the biggest artery in the body. So when the blood is going out through the aorta, it is with a lot of pressure so that blood can reach the head or can also reach the very ends of your body. There is the toes, we also have the fingers. These are the very peripheral points of our bodies. Blood must reach there. So for it to reach there, we need high pressure. But remember, the blood that entered the heart didn't have much pressure. It only gained the pressure through the contraction of the arteries, of the ventricles, when the cardiac muscles contract, that is the ventricle muscles contract, then they push the blood out through, through the aorta at very high pressure, or even to the lungs to collect the blood at very high pressure. So for us to understand the heart, we require this. This type of a physical item you can be able to see is an example of a model, and this type of model that you can be able to see is what we call an analogy. So we have several analogies, I'm sure, around. You can try to imagine of any that you think can be used to describe a certain maybe explanation of whatever is happening. Try to imagine of any. Another one I can talk about is you have heard of very talented doctors. Like if you have ever heard of Benard in America, who was a neurosurgeon. That is a very talented doctor, a very bright person. We also have these people who deal with the head, the brains, neurons, the brain, very delicate points. But now, you and me, at one time, we have tried to imagine, how does the brain work? Just imagine you listening to me. The brain is getting it through the eye. The brain is getting it through the ears. That brain is going to store that information. And if a question is posed that explain or state any two types of models, you will be able to state where are you getting that answer. You are retrieving it from somewhere, which means it was stored somewhere. You have a hard disk. So I'm already using something that you must be aware of. That's a computer. So you can use a computer as a visible model to describe your brain. That this computer has these areas you can use to feed in information. You have a keyboard, you have a mouse, you can use them to feed the central processing unit with information. And once you have fed the central processing unit with that information, the information can be kept. Just like your eye, your nose, your ear feeds the brain with information. Once it has been fed with that information, it interprets the information and stores the information in particular correct positions. Just like in your computer, you will not just store every information in one particular point. You will say, may I create folders? This folder will carry this. This folder will carry this. And in fact, even some folders, you will add on some log. So that for somebody to enter, you need to have a password for the same. Even your brain has such. There's some information. For you to get back that information, something must happen. That is, a password must be gotten. For example, can you remember at one time when you interacted with a very awful smell? Having mentioned that, you can still remember the smell as if it is there. Or a very nice smell. Maybe somebody passed by with a very good perfume and you liked it. Can you still remember that perfume? I'm sure you are now getting it. As if it is now there, when it is not there. That is, you have just opened by pressing a certain password in that computer of yours, which is the brain, and it retrieves how the brain interpreted that smell at that particular time. So, a computer is an analogy to our brain. That water pump is an analogy to our heart. That is the type number 1 of models I will want us to understand. So the second model is what we call the third model. Number 2 is the thought model. So we have the thought model and the analogy model. Thought coming from thinking. When you are thinking, it means you are not doing physical work, but you are working. The work cannot be seen, but you are working, you are thinking. And in thinking, you try to describe that thing or get that description of something in a particular way for better understanding. Somebody can easily ask you a question, and before answering, you will answer by saying, please give me some time to think. I've just asked, which type of meal would you wish to have for supper? And since you like so many types, you will tell your mom, please give me some 5 minutes to think over that, so that you can scrutinize in all the types of meals you like, which one you want. But will your mom be seeing you touch this and that to choose? No. So when it comes to a thought model, it is an imaginative model. You imagine an imaginative model. Maybe to put ourselves into a proper view of this, we have all heard of the universe. You have heard of the universe? I've also heard of the universe. Who was there when the universe was being made? None. Because we are told the universe is as old as 13 billion years. 13 billion years. Billion years. Now, who was there when it was being created? And who is there in a particular position to categorically say, here is the sun, and these are the stars, these are the planets, and even on this planet we have moons. For Earth we only have one moon, but other planets have more than one moon. Who is this person at a particular point to see that this one is this way, this one is that way? The way you are looking at me, you are seeing me, so you can be able to describe me. But the universe, can you be able to see it? No, you cannot. But we have models. We have atlases. You will see maybe in the table of contents the universe. So you will open to that page and you will get a proper picture of the universe. How was the picture gotten? It was gotten through imagination. We are also told that these not billions but millions years, these so many years, when the universe was made, it was made through a Big Bang, which is gotten as a theory, Big Bang theory. And in fact, it is also demonstrated in a way. So that kind of demonstration on how the earth was formed through the Big Bang theory is what we can call a thought model. You are trying to imagine, you are thinking about it. How was it formed? How did it come into being? And through this model, one will always be able to explain to those who are even very hard to understand, at least now to get it. You will realize that, okay, so through this model, so we have a sun. And around the sun, we have planets that move around. And these planets are of different sizes. We have big ones, we have small ones, those that are closer to the sun, and those that are far away from the sun, and so on. And we have even the stars. The sun is not the biggest star. It's just one of the stars that is close there to our planet. But we have even bigger stars very far away from us. How do we get that? that is gotten through a model. So remember, the example I'm giving is a model of a very big thing that you cannot be able to comprehend just that way unless something that is more tangible, like a model, is used for you to understand. So a model can be used, a third model can be used for one to understand a very huge, a very incomprehensible, big by magnitude item or system to become so easy and well understood the way now we understand our universe, that we now have 8 planets and so on. Again, this thought model can be used to describe a very small thing. Very small thing. For example, when you want to understand something like how a virus or a bacteria is transmitted from one person to another, can you be able to see a virus? You can't. In fact, we have some particles that even a normal microscope cannot be able to see, such that you require a very powerful microscope, what you call an electronic microscope, for you to be able to see such small particles. But they are there. You will feel you are sick. And why are you sick? Because of a very small thing by the name a bacteria or a virus, what we call disease-causing microorganisms. But now you want to explain to a crowd of people who may not be in a position to understand that idea, that aspect you want to explain properly, on how they should be very careful with their hygiene. You are talking about a viral disease. We heard of influenza virus, you have heard of it. So you want to explain to them that hygiene is important, and in case you are not hygienically fit in a society, you will easily kill the whole system by spreading your disease to others. Then one will wonder, but I'm here and I'm excluded from the others. They are about maybe 10 meters, 20 meters or 100 meters away from me. How will I infect them? Using a model, you can be able to draw or make maybe a bacteria. This may be a bacteria, and there may be so many of them in the air. So this object, which can be, for example, in a balloon form, you can have a balloon in a particular shape to show a bacteria. Then you demonstrate this balloon being filled in with a gas that is lighter, Then you release this balloon or balloons. They can be so many. Remember, when you are talking about disease-causing microorganisms, it is not just one. There are so many. But you can as well talk about one which can subdivide into so many. Now, having the so many, throw them in the air. This is a model. What will happen? If it is a windy day, they will be carried to a particular direction. So, by so doing, you can describe, here is a person. Who is you? Releasing these disease-causing microorganisms through maybe a sneeze, an open sneeze. Where is it? It is now to the air. But it is now windy, and the wind is carrying these bacteria to that direction. What will happen to this person? Maybe it is the boy who was sneezing, but this lady is around 50 meters away. Do you think this bacteria from this gentleman can reach this lady? Obviously, yes. Why? Because the wind is assisting in carrying the pathogens, what we also call germs, but the best is disease-causing microorganisms to that lady. So by using this model, you will have described a very small thing which cannot be seen by our naked eye, or sometimes even our simple microscopes, to explain to those people who could have had difficulties in understanding this, and now get it that, okay, so sneezing openly, I will release whatever I'm having within me, which is harmful. And because they are light enough, they can be carried by wind to other areas. And those other areas will have other people. And these people will get the disease-causing microorganisms, and they will start ailing the way I'm ailing. That is a third model. Another thing that is very common now that we are talking about chemistry, this may be to do with the biological side. How about in a chemistry class where we are? It is science, but a sub-branch of science called chemistry. In chemistry, we mostly talk about small particles, very small particles. As you proceed on, you'll learn to get to understand much better this particle I'm going to mention. So in chemistry, there is something we call an atom. This is a very small thing, smaller than a cell. You learned in a branch of science called biology, the smallest particle that has life anywhere is a cell. The smallest particle unit that has life is a cell. But still that cell you cannot be able to see. And within that cell there are so many atoms, because remember, in a cell there are so many organelles. We have the nucleus, ribosomes, rough endoplasmic reticulum, and so many. And inside that nucleus we have nuclear materials, RNA and DNA. And that DNA is made of atoms. So you can imagine how small an atom is. But remember, we have to understand what is an atom, because what an atom does is a lot. As much as it is that invisible, what it does is a lot. So we need to understand this atom. How do we understand? We have to create a model. Another thing, maybe in chemistry, the most common thing we always see, water. What we wish to understand, how does this water transform itself in these three states of matter? For us to understand, we need a third model, because that water, as you can see it, if at all wherever you are seeing water, it means so many molecules of water. And one molecule of water has only 3 atoms, 1 oxygen and 2 hydrogens. 3 atoms, 1 oxygen and 2 hydrogen atoms. So it is very small. But the so many small come together to form what you can see as water ice, water liquid, or water vapor. 3 states of matter. So we normally use third models to describe such small things that cannot be comprehended easily to be well understood. Now, I said there are 2 major models, but indeed we also have another model that in one way it falls under a third model, but because of the way of its description, we can specifically put it in a different way of labeling or stating, so that it gives somehow a difference between the third model and that one, and that is the particle model. Particle model. Now this particle model is under third model, but since this one is specifically going to talk about particles, and particularly particles that are small in size. Particles small in size. Particles small in size. This one was not just talking about particles. It can talk about living organisms, which you can also call it a particle. If you so wish, like a virus can be called also a particle, but a bacteria cannot be called a particle. Fungi cannot be called a particle, and all that. So because of that, when you talk about the third model, it involves all such. But for particle model, it specifically deals with the non-living organisms and how they are made. So that's the slight difference between the particle model and the third model. They are all to do with the thinking. But this one is a bigger set, and this one is a subset of this one. In this one, you can describe this, but in this, you cannot describe this. A good example, I use the disease-causing microorganisms. That one will fall under third model, but it cannot always fall under particle model, because these disease-causing microorganisms can be found in a single form. You can talk of a single virus. You can talk of a single bacteria. But when you talk about particle model, you are talking about so many particles together. So let's look at the particle model. In the particle model, we are looking at small particles, that is in size, and these particles are packed together. Packed together. The small particles are packed together. So the packing issue, the packing effect of these particles now brings in an aspect of bonding. You cannot be close by with something else if there is nothing to do with that item. That is, there is no bond between you and that item. For example, after this class, assuming that this is the last class for the day, you will break off to your various homes. Each one of you will go to his or her own home. Why don't you go to the other home? And even if you go there, you will only be going there because of one reason, a friend. So which means there is a bond. You will not just go there for the sake of going. You will go there because this person you are accompanying to that home, which is not your home, is because this person is your friend. So there is a bond. If that is not the case, you will go to your home where you have your parents or your guardian. Why? There is a bond. What am I trying to say? When you talk about these small particles packed together, they are packed together because of a certain force of attraction. And it is that force of attraction, it is that packing of those particles that makes them behave in the way they behave. But remember, these particles are small. So we cannot easily comprehend on how they behave. I've said for them to behave the way they behave. But that is the behavior that I don't know. So how do I know? I will need a model. And that model, which is a particle model under thought model, will make me be able or easily understand that description. So to give maybe a good example of this, for us to see what is a particle model in relation to a thought model, let's look at water. let's look at water and how this water goes through these three states of matter. So water can exist in three states of matter. We have the particle model of water in the three states of matter. So that is our point of interest to assist us explain a particle model and a thought model. Starting with the solid, then liquid, then lastly gas. In a solid, we have, let's have our model in a box form. Remember I said that the model is something you can feel, you can see, you can interact with. It can be physically an item like this one, or an item like a drawing, like what I'm doing. This is a model, a drawing model, a drawn model. So in solid, the particles are closely packed. The particles are closely packed. Now, when it goes to liquid, the particles are close, but not as close as in a solid state. So we can have it this way. And in gas, the particles are far away from each other. Maybe you can have it this way. So this is a model, and the model is helping us comprehend, understand these very tiny things that we only feel they are being there, but we never know or understand how they are behaving for us to see the way they are doing it. Like when you see ice, do you ever ask yourself, what has happened to the water for it to be in that solid state, the way it is? What is so different between this, which is a solid, and maybe your blood, which is a liquid? What is so different between this air? You can feel the air, you can feel that wind, but you cannot see the wind. Those are the questions this model can be used to explain. So let's see. When you see particles being clamped together, packed so close, and being so close, then you call it a solid. What does it mean? It means that in solid state, these particles have very little energy. In comparison to liquid, the liquid particles will have slightly more energy than the solid. So meaning that particles in gas will obviously now have more energy than the two other states of matter. Which type of energy are we talking about here? We are talking about heat energy. And now that's why by either increasing heat energy or reducing heat energy to water, you make it change from one state to another. Now, what does the heat energy do when you are either increasing or reducing? The heat energy, when you increase heat energy, you make the particles to start moving more and faster. Just like You, during a very cold period, very cold, you rarely move so much. You just feel like remaining at one particular point. You feel you don't have the energy to do all that work. But how about during summer? During summer you will be everywhere. Why? You feel you have more energy. Look at a situation like, for example, you have just had your meal. You will have more energy to move around. But a situation where you don't have enough food in your body, that food is representing the heat energy. No food, no energy, no movement. With the food, more energy, there is a lot of movement. So the same is applying here. When you increase heat energy, the particles vibrate more. And when you are vibrating more, like when you are, for example, on a floor dancing, if you are so vigorous, your friend will tell you, please, can you move a little bit far so that now you can improve your dancing style. You are so vigorous. And she will or he will also move a distance a little bit. That is creating a space. Because you have more energy. You are dancing more vigorous. But if you are your dancing is that, slow motion, you don't require a lot of space, so you will be close by. What we say, particles in solid state vibrate in fixed position. Particles in solid state vibrate in fixed position, making a solid now to have the properties we know of having a fixed shape. You remember in the previous lessons we mentioned that fixed shape, you cannot compress this because where do you push the particle to? They have touched each other. It's like this one and this have touched each other. Can I push this one closer to this any further? No. They have touched each other. So you cannot compress this. You cannot make it to flow because it is rigid. So those properties can now be well understood, well explained using the model that particles are closely packed, vibrating in fixed position. So it is also telling us something, that particles in nature are always in motion. All particles in nature are always in motion. But some you don't feel that are in motion because they are in solid state. But their motion is only vibrating in a fixed position. Somebody can easily object to that, maybe to give you a good account of a solid being in motion. If ever you have been along a road and a heavy truck passes by, you may hear some buildings show some vibration. For example, the iron sheets produce a certain sound. But if you look at the building, you are hearing the sound, but you cannot see the building shake. What is that? The particle is in motion. It's only that your eye cannot catch the motion. If you ever see a mosquito or a small insect, a fly, a bee flying, do you see the wings vibrate? You don't. You cannot be able to see, but they vibrate so that as it flaps, it can now move the way it wants. So the same to this. When that solid is vibrating, it's only that your eye cannot get it, but all solids vibrate. Liquids, being that the particles are far apart because of the high energy, it gives us the properties the liquid has. One, it flows. You can pour out water. Why? It is flowing. And why is it flowing? Because the particles are not close by. They are free to move and move more than what you can see in a solid. In fact, we say particles in liquids roll over each other. They move until they are able to roll over each other. This one cannot roll, but this one can roll. So by rolling, that's why a liquid can flow. As it is flowing, the particle is rolling on others as it goes down. A liquid will take the shape of the container. How? They roll over each other until they settle at the bottom of the container because of the movement. How do you understand that? Particle model, that in the liquids, particles are slightly far away from each other, and therefore it shows that the bonding force between the particles is a little bit weaker compared to that in solid state. Compressing. Liquids cannot be compressed, but some other liquids can be compressed. Some other liquids can be compressed. Why mention of other liquids that can be compressed is because when they have these spaces big enough being available, then they allow the liquid to be compressed. They allow the liquid to be compressed. And maybe water is also a very good example to explain this. Remember, ice floats on water. Ice floats on water. Why? Because water in liquid state at 4 degrees centigrade, water compresses itself until it is so compact that it gains the highest density. It gains the highest density. So water at 4 degrees centigrade, it has the highest density. It has the highest density. And having the highest density, it means water at any other temperature less than 4 degrees or more than 4 degrees, it will be less dense than water at 4 degrees centigrade. So this makes ice, since the ice will be at a lower temperature than 4 degrees centigrade, it will be at a lesser density. Why? Because ice expands. This is only unique for water. At this level, you may not understand everything to do with why water behaves that way, but as you proceed on with the science classes, you will be able to understand why water behaves the way it does. It is the only liquid that does that. In a solid state, it expands. So in that expanding, it occupies more volume, and in occupying that volume is when it floats on water. We could have expected ice to sink, but instead it floats on water. Let's look at water vapor, steam. That's still water, but in gas form. What happens to steam? It goes up everywhere. Why? Because particles in gas state are held by excessively very weak forces. In fact, some argue that in gases there are no forces, but there are, but very, very weak. Very weak. We call them molecular forces. Now, being that they are very weak, they allow gaseous particles to move very fast and to all direction in a straight line. Particles in gas state move in all direction, but in a straight line until it hits a surface or another particle. It can come and hit this one. Then, as it hits, it will bounce either back or deflect to another direction. So maybe take this direction. It can still go hit another particle, gas particle. As it hits, it will take another direction, maybe this direction, as maybe this other one takes the other direction. This is what gives us that description we call the Brownian motion. You will learn it in the next class, where you will be describing the Brownian motion of gases and even have models to describe the Brownian motion, because some will not understand it. But using models, we are talking about models, you will be able to understand the Brownian motion. For now, our interest is to see how that gas particle is, how far it is from the others, and how that aspect of being far from others makes the gas to have the properties we know as we learned in our previous lessons. For example, one of the properties was gases can be compressed. Why? Because look at where the particle is, far away from one another. Because of that, you can force by increasing pressure the particle to go closer to each other. Assume this container is being compressed. As you compress, you will be pushing the particles to move much closer to each other. That confirms to us that gases can be compressed. Gases also fill the whole container into which it has been enclosed. How? Using this model, we can now comfortably say, since this particle has a lot of energy, and by using the energy, it moves to all directions and very fast, hitting each other on the way. If in that class, you are maybe 10 of you in that class, and I ask you, instead of being seated like now in a solid, start walking around. You will still knock around each other, take some shapes. Maybe in sitting, you have taken a certain shape of that class. But in walking, you will start now deforming the shape, because each one of you will be moving to his or her own direction. But now imagine I say start running. I think we shall have chaos. You will start knocking each other. In walking, you are negotiating the bends very well of maybe your table or corner, chair, or whatever item, seat, whatever item you are using. You are negotiating over them very well. But how about if you are running? You will be knocking them. As you knock them, they will also move. As you also fall on the other side, as you fall, you are moving. You will hit another one. Somebody else will be maybe jumping. And in so doing, you will be filling the whole room, as compared to when you are walking or when you are seated. You will reach other corners that if you are told, can you go to that particular corner or that particular corner, you may not be willing to go to that corner. But if you are hit by your friend or you are pushed to go, will you not go? You will go. So you will end up filling the whole container. And that is how the model of a gas can be used to describe how gases fill the whole container in which they have been packed. And so many other descriptions you may want to describe about gases, liquid and solids. So models are there to help us understand what we think or what somebody thinks is not possible to be understood plainly. Now, we have just been talking about the model of particles, the model of particles, that is a particle model. And we have used water as an example. And for information, this is the biggest particle model anyone will always use, irrespective of the level of study, because it's the easiest and the most interactive we have, but it's not the only one. We have even more complicated ones that you can use. But we need to understand that we also have theoretical points. We have theoretical points where we always assume at that particular point there is no movement that can take place. And it will be very wrong for us to talk about all these and we fail to mention that particular point. And that is at absolute 0 point. Absolute 0 point. That is negative 273 degrees centigrade or 0 Kelvin. We have two units we can use in measuring temperature. You remember in our previous lessons we talked about units, and that is in either Celsius or in Kelvin scale. In Celsius, we have negative 273 degrees centigrade, and in Kelvin, we have 0 Kelvin. At this temperature, any substance that will reach this temperature, it is assumed, I'm using the word assumed, that the particles in that substance are no longer in motion, not even a vibration like the one we have seen in solid state. And this can, in a way, be able to be explained using, probably, if you have ever watched a movie, there's a movie I've once watched of Predator, where a metal is exposed to liquid nitrogen. Liquid nitrogen. Remember, nitrogen has a boiling temperature. Nitrogen gas has a boiling temperature of negative 196 degrees centigrade. So, if you are talking about liquid nitrogen, it means this is a liquid that is at a lower temperature than negative 196 degrees centigrade. So, when you expose some metals that are thought to be very strong indeed, to such an extreme temperature, it just easily breaks. It brutally breaks. So in that film, The Predator, that Predator was exposed to, it had to collide with a tank that was carrying liquid nitrogen. On that nitrogen pouring to that Predator, it had to break into pieces, and yet it was metallic. Why? Because at that temperature, the the substance is assumed to have particles that are not vibrating. And if you are not vibrating, you are not ready to move. You are not ready to move. If you force a little bit to move, then you break. Just like glass. If glass is rigid at one point, you try to push it, it will not move. If you force it a little bit, it will break, and break brutally without warning. So that is a characteristic of energy in particles. And to understand all of this, we always require models, as we have just learned. So class, we have been looking at a very important aspect in the world of science, an aspect that is always used to save millions of shillings. It is through models that scientists test very complicated machines, very complicated situations, very complicated environments when constructing or making items to deal with those conditions. For example, if you want to construct a very big Airbus, this Airbus will be going through so many conditions like high pressure zones and such. Before you construct that plane, which is very expensive, costing billions of dollars or millions of dollars, simulation must be done of that Airbus in a condition that we call a model. If in the model the plane will navigate all those conditions very well, or maybe a ship manipulate itself in a very serious sea condition, or a warplane manipulate itself in such conditions very comfortably, to the satisfaction of the engineers, of the doctors, or whoever are dealing with those items, then it makes them to qualify the item to be constructed, so that when it goes to work on the material day, you don't lose those billions or millions of dollars. So always go for models for better understanding. In our next lesson, we shall do more of the explaining on how states of matter changes, on how substances change from one state to another, just as we have seen from solid to liquid, liquid to gas, or vice versa. Until next time, thank you.